Okay, so let's have a go at question 1. So we start off with finding the reaction at A. We have to define a few things here. So I'm going to define X to be going in this direction. I'll define my reaction to be going from left to right. And the law that we'll use for the majority of this question will be when you sum the forces in the X direction, we expect them to be 0. So let's apply that to A, to the external forces, which will include the reaction. So I've got RA, take away 50, going opposite direction, plus 20 equals 0. So RA is going to be 30 kilonewtons. Part B. Calculate the internal forces and stresses, sections A, B, and BC. Now what we want to do here is make cuts. And it's best to go from right to left. The reason for that is because our RA was an unknown from the question, so I might have gone wrong here. So to avoid that, let's go from right to left. So the first internal force I come across will be this one here. You make your internal force always point towards the cut. So that's going to be the internal force FBC. And we, essentially speaking, just look at this section here. So we look whatever's inside this grey box, and we're going to apply this sum of the forces for that case. So that will give us minus FBC plus 20 equals 0. So that gives us FBC equals 20 kilonewtons. Okay, now let's do the same thing here, where our internal force will be FAB. And notice that my FBC's are cancelling out, or I don't have a cut. You can use either argument, valid. So we only have minus, let's go and do that in green, blue. So we only have minus FAB minus 50. I'm going to skip the FBC's and plus 20 equals 0. So that becomes a minus 30, plus 30 and minus in the end. So minus 30 kilonewtons. So that's the internal forces done. Obviously the stress is straightforward. Stress equals force divided by area. So we want to apply that to these two terms. So stress BC is going to be 20,000 divided by BC's got 20 diameter, so pi divided by 4, 20 times 10 to the minus 3 squared equals, and this one here, I'll do the same. So the stress AB, let's keep this sign, might be useful, so that's in compression, 30,000 divided by pi over 4, and that's got 30 times 10 to the minus 3 squared. Let's work out these numbers. So the top one, 20,000 divided by pi over 4 times by 20 minus 3 squared, close the bracket, Press the Eng button. So we get 63.662 times 10 to the 6, or actually it's right there, megapascals. Okay, and now let's do the next one, minus 30,000. And that's 30. So minus 3, square it. So that would be minus 42.441 megapascals. Okie dokie. Right, so that's all of B done. Now for C, for the displacement. I want to refer to your formula sheet here, but displacement is going to be the sum of forces, internal forces, and the lengths of their particular sections divided by the Young's modulus of those particular sections and the cross-section area of those particular sections. So we've got F AB, length AB. Our Young's modulus is just a constant 200 megapascals, so I'll put that down as E. And area AB. Plus the next one, FBC, length BC divided by E, and that's ABC. So, actually, so if we notice a trick here, F over A is stress. So we could rewrite this as stress AB, length AB divided by E, plus stress BC times by LBC divided by E. So probably going to need a new page, but might be able to fit this all in one line. So we take our stress, AB, so that's this one here. I had it. Yeah, I still got it. So let's multiply that by its length, 250 millimeters, divided by 200 gigapascals. And the next one is the BC, so that's this one here. So that, notice I'm using the signs. So the AB section I'm expecting to get compressed a little bit, and the BC section I'm expecting to get extended a little bit. So plus 63.662 to the power 6 times by its length, 250 again, divided by 200 gigapascals. So overall, let's do this in millimeters. So overall we get 0.0265 millimeters. Okay, so parts D and E is looking like I'm going to need a new page. Quite a lot to do here. So let's go to a new page. Okay, that'll do. Right, so calculate the reactions of A and C. Well, that's a bit tricky because I've got only really this to work with at the moment. I've fixed location C, so this is now, imagine that I've got a kind of wall at that position. So we have reaction RA, and we have another reaction, bizarrely, at a point where we're actually applying a force, which is a bit weird, RC there. So let's apply this rule. So we've got RA, take away 50, plus 20, plus RC equals 0. So I can say RA plus RC equals 30 kilonewtons. What else can I do? It's a bit tricky to solve this problem without first finding the internal forces. I wonder if I can avoid doing that. The next thing to try is to do the same game as we did before. Let's take cuts through the body here. So we're going to take a cut through here, and when we do that, we have an internal force. We'll go same direction as we went before, although there's no reason to go left to right this time because I've got two unknowns either end. So I just look at this grayed out section and then sum what I've got. So I've got minus FBC plus RC equals 0. Okay. No, I've forgotten something, haven't I? I've forgotten the 20 because it's hidden behind that scribbles. Plus 20 equals 0. Okay, so let's write this as FBC equals RC plus 20. Next, let's do the same thing here. Okay, so we're just looking at this grey section. The internal force that we're using is now FAB. The one on the left I ignore. So that will give me minus FAB minus 50. These two will be cancelling out. Plus 20 plus RC equals 0. So that's FAB equals RC take away 30. How can I find reactions without finding the forces? It would make more sense to me if part E was first. Let's carry on. So the only other equation I can use is the fact that the extension of the bar, let's say for example at C, is going to be 0. It's not going to move. So if I sum up how these two sections are going to move, like I did before, this, in this case, will equal 0. So therefore, I can say that FAB LAB over E is just a constant, so we'll just say E, and then we've got AAB plus BC, length of the BC bar, EABC equals 0. So nothing particularly exciting there. You can rearrange it and you can say, for example, that FAB is going to equal minus FBC. These you can see will cancel. LBC over ABC, and then I'm going to take these, multiply them through So you're going to get things to be just ratios. A, B, and L, A, B. Yeah, so you notice that you've got false, false, and then obviously we've got ratios of lengths. LBC divided by LAB, and the area AB divided by the area for the BC length. Now these two lengths are the same length, so the first ratio is just going to be 1. The second ratio will be the fact that this is wider. I can base it on the diameter, so I can say that FAB equals minus FBC. The area is proportionate to diameter squared, so that is going to be 30. I'm going to even drop my millimeters here, so that's going to be 30 millimeters squared divided by 20 millimeters squared. So, I've been a bit naughty there, dropping the units, don't need them, got a ratio of millimeters. So that tells me that minus FBC is going to be 9/4. Right, how does that help me? So I can replace FAB in this equation here. So let's do that. So let's call this equation 1, this equation 2, this equation 3. So equation 3, we're going to replace it with that term. So that gives me, my battery is low. Am I plugged in? Sorry about that. Right, hopefully that's okay. Right. Right, so we're going to substitute that into that equation there, and that gives me minus FBC, loads of horrible algebra, 9/4 equals RC minus 30. I'm trying to get rid of internal forces. So just more horrible algebra. Multiply this through by 4/9, and that gives me minus FBC equals 4/9 RC minus, does that give me anything nice? 30 divided by 9, no, times by 4, 40/3. Now, if I take this equation 4 and add it to this equation 2, the FBCs go. So let's add those two together, and then that gives me 0 equals 1 plus 4/9 RC. And this is a negative. and I need to add on 20. And so that will be plus 20 over 3. So RC will be minus. So it becomes minus divided by, don't bother with the fraction, 4 over 9. Let the calculator work it out. And that gives me minus 60 over 13. And of course we are engineers, so we should press the Eng button. And that will be minus 4.615, and that's kilonewtons. Okay, now I can go back to equation 1. RA equals, see, I had to do a little merry dance there to get rid of all the internal forces. In a way, it's easier to work out the internal forces and then go back, but hey ho, let's do things in order. So here we're now going to go back to this equation here. So that's going to give me 30. Take away RC, which becomes a plus. Plus 4.615. Yeah, I could have done that in my head. 34.615 kilonewtons. So that's part D. Part E is calculate the internal forces. Well, now I've got all this data. It's relatively straightforward. I can use equations 2 and 3. Equation 2 is FBC equals RC plus 20. RC is minus 615 plus 20. So minus 4.615 plus 20. So it gives me 15.385 kilonewtons. Okay, let's go to this one here, FAB. That's what again? That's RC. So, what was the RC? That's the minus 30. Okay, I can do that ahead. Minus 34.615 kilonewtons. So that was easy. How does that compare to previous results? Yeah, it's getting really hot. Okay, so previously we had a 20 and a minus 30. 15 and a minus 35. So similar. So the stress for BC is going to be 15.365 divided by pi over 4. BC is 20 squared. So what's that? 15385 divided by pi 4 times by 20 to the minus 3, square it. So that becomes 48.972 megapascals. And here AB minus 34615 divided by pi over 4. It's the thicker one, 30 times 10 to the minus 3, square it, and that's going to be what? Minus 34615 divided by 3, square it. Ooh. Should I have expected that? Minus 48.97, it's the same answer, megapascals. Okie dokie. So let me know if I've made a mistake and I will correct it and do an update. I don't have the solutions. Is that what you're getting? Let me know.